Hello students, today we will be discussing about the low probability of intercept communication systems, their design, and what is the meaning of this low probability of intercept, what exactly we mean the detectors for this low probability of intercept communication systems is the point of discussion today. Let us start with the understanding of why do we require to design a low probability of intercept designs. When we design such communication link of LPI, of having LPI, we already assume that there is a requirement for this kind of system to operate in such an environment, to operate in a hostile environment where there is every possibility that enemy will try to detect the transmitted signal between a communicator and a receiver. A very good example of such communication system or a such hostile environment is such that when we communicate from a surface vehicle to the satellite, where the surface vehicle transmits via very short messages to the satellite, which is a receiver to him, and suppose some enemy aircraft is moving around and trying to actually intercept or detect the presence of this RF energy corresponding to the transmission that is going on from surface vehicle to satellite. Another good example will be the underwater communications, where actually from the intended communicator to the receptor the communication is going on, and some submarine or the enemy submarine is trying to detect the communication signal. Remember here one thing, I should mention one thing here, that the interceptor who is trying to intercept your intended communication or legal communication between communicator and the receiver, the performance of such interceptors is determined by his ability to determine or detect that there is a presence of RF energy corresponding to this transmission. Remember what will be done after that detection. For example, whether you will try to find out the location of the communicator as well as the receptor or the receiver, or we will try to decode the message or not. That doesn't actually, whether we could decode the message or not, that actually doesn't define anything about the performance of the interceptor. Performance of the interceptor always is defined by its just detection ability of that energy. So basically, if I now try to gist up, so interceptors are ordinarily they try to acquire some communication information. For example, in which frequency band the communication is going on, what exactly is the modulation format getting utilized, what exactly is the modulation format being utilized, frequency band, what the modulation format getting utilized, whether there is a space spectrum communication modulation going on, if it is, and what is their characteristics of that modulation. And also it tries to capture the information like what is the space bandwidth utilized and what is the hop rate that is being used in the actual communication system. But remember, it cannot give you any information about the time of the message initiation or what is the secure code that you are utilizing from the intended communicator to the receiver. So the interceptor's detection strategy, in that sense, it is limited to the detection of the energy of the transmitted signal, or I can say that it is some form of energy detector finally will be a form of a interceptor. And truly speaking, for any kind of the scenarios that is posed for the communication system design, and the extent to which these interceptors or the energy detectors they can improve their detectability will largely be dependent upon the cost and the complexity you are involving in that detection process. So we understood that interceptors will be basically the energy detectors. Their detectability will be dependable on the cost and complexity involved, and hence another part is there the simplicity in their implementation, and based on the optimum theoretical performance that this detector can give. Based on that, we will discuss today the various types of the energy detectors or the interceptors present for who can actually detect the signals in such scenarios. The first and foremost, the communication side. When the original communicator is communicating with its receiver, he has some responsibility to remain or maintain as low as a visual profile as possible even when he is not communicating with the receiver, to make the system, the whole system, a low probability of intercept communications link. The communicator has some responsibility to maintain this low profile of visibility. He can also keep this low profile of visibility. Even actually his location should be concealing. And when transmitting, such communicators are expected to transmit with a radio detectability with a reduced power, reduced radiated power, so that his detectability is reduced. And there are several techniques that the communicators use to have this profile. Number one example may be actually he can utilize the low side lobe antennas, where actually such that the main lobe gain will be extremely high and the side lobe gains are such low that any intruder who is trying to get the signals or detect the signals, he cannot actually get any information by reading the side lobe signals. And communicators can use the maximum, they can use the maximally the channel coding to minimize the transmit power level, which will be necessary for the proper message detection. He can also the receivers can also be designed in such a way that an optimum performance receiver or the receiving system is designed. Very low message bit rate also can be utilized, and the very shortest possible message lengths also can be utilized to go ahead with. Next, the communicator receivers, as we understand that he will be utilizing the anti-jam techniques like the spectrum modulation technique. And remember one more thing, though these are all the possibilities of availing a low probability of intercept communications between a communicator and a receiver, please remember that all at a time cannot be attained from the communicator side because of the various degrees that extend from the space as well as the time and the availability of all that reduced processing power of the receiver as well as the transmitter, and lot of other issues, system related issues. And we should actually say one more thing, in order to actually get a resilient against the interceptors, sometimes the communicator receivers also try to they attempt to jam the interceptors if they can locate that there is a presence of an interceptor, and if you can locate the location information about that interceptor receivers, the receiver, intended communication receiver, also can try to jam it. So from the side of the jammers or the interceptors, here they should also be aware of the fact that the receiver can intentionally send some information to jam him and to make him confused about the actual communication that is going on. So when interceptors will be designing his own circuit, he should be aware of the possibility of getting jammed by the actual transmitter receiver system. And when we will design a intended communicator receiver system, and then we should be able to keep our profile and the location as low as possible. So when all of these above factors are individually contributing to this LPI, as I mentioned, that all cannot be realized simultaneously, and we will try to see here some of those characteristics that will help us to design some low LPI, low probability intercept communication systems. There are several variables of this nature that may include some applications that we are trying to say here. Suppose the transmission elevation angle, antenna elevation angle, when it pointed to the communication receiver, and what exactly is the elevation angle we are fixing with, depending upon that actually whether interceptors will be able to intercept you or your signal, it depends. For example, when the elevation angle will be very high, and it means that this lower side lobe gains will be very low, again hence actually your possibility of getting intercepted will be low. And at the same time, the main beam intercept, the possibility that the main beam of such high elevation angle and with high elevation angle antennas, the main beam intercept at far range will be also obviating. It is not possible actually in aircraft to intercept your main beam signal also in that situation. So it is in a gist we can say that high elevation angle pointing out towards your receiver can make you a possible low probability of intercept solution. Second thing is, but it's not, sometimes it is not actually totally in your hand, it's a lot of the other stuff that are related to the calculation of this elevation angle of an antenna. Secondly, it depends on the fact that whether satellite is receiving the signal from a high spot antenna or some high gain antennas or a moderate gain antenna, where we call it the earth coverage antenna, if the communication is going from the surface to the satellite. Also the weather condition between the communicator and the satellite, and which may be different for the link between the communicator to receiver, communicator to the satellite to satellite, it may vary also. So there are some issues involved which will also control whether you can design at all a LPI system or not, and if you are able to what extent you can design it. Remember, when we use the spot antenna or a high gain antenna, it is equivalent to getting a very clear weather, because you are getting a very high gain at the receiver end. The remaining part that we have to deal with the issues and the answers are the trade-offs among the modulation, coding, synchronization techniques that can be used in the communicator, and the sophistication of the detection techniques that will be employed by the interceptor also. Based on that also, how good the LPI system is will be depending on. Some viable options which are available for the interceptor to improve its detectability is to use multiple narrow coverage antenna receiver combinations that will acquire the gain by individually covering the fractional portions of the total search areas on the spatial domain, and in such way actually your detectability will be definitely improved in the interceptors. But remember, your complexity will be very, very high, because huge number of the detector circuits you have to deploy when you are having a narrow coverage filtering activity over the spatial domain. And but here we will be mainly focusing on the issues that we have asked. We will have a direct bearing on this system design issues that we have defined earlier slides. And let us understand what are the very common factors in a LPI communication link we use. We will start with signal modulation forms. Remember, whatever the points we are going to discuss from now onwards, they are all actually to enable the LPI system we are discussing about. So that the LPI is enabled, LPI application is enabled. From the communicator side, the signal modulation format, the most popular signal modulation format, we prefer to go ahead with a MFSK system, with an MFSK modulation scheme. And using MFSK, we have described our frequency hopping communication system. Hope we will remember. We have also whenever we have designed our combined or hybrid communication system, also we have talked about MFSK a lot. We will revisit the signal modulation format once more here. We understand that for the ith transmission interval, where the transmission interval is given by ITS 2i plus 1 ts. The modulated MFSK modulated transmitted signal ST will be looked like the equation 1.1, where this S is the transmitted power and F0 is the center carrier frequency of the transmission. Phi I is the random phase associated with the ith transmission, and del f is equal to your k into ts. The k is a integer. It is a frequency spacing basically between the tones of this M array set of the frequencies, from where actually you are randomly picking up the frequency to transmit your transmitted signal. And di is the value of the transmitted data symbol for the ith time in instant, and this data symbol is also picked up from the set of the integers. So you have basically an M array set, and M array frequencies are actually allotted to carry your data signals. So we have seen this form earlier of this MFSK. We have just revisited it here. And in order to reduce the chance of interceptor detecting that your communication is going on, and to combat and also to combat jamming, we prefer to go ahead with a combination of different kind of the space spectrum modulation systems. We prefer to go ahead with only frequency hopping, or a combination of a frequency hopping with a time hopping, also frequency hopping with sometimes with a direct sequence space spectrum communication systems. So there are basically the four more popular employed LPI systems transmitting that MFSK data modulation. They are the frequency hopping, and then there are the frequency combination of frequency hopping and direct sequence system, hybrid system designed based on the frequency hopping and time hopping, or the frequency hopping, time hopping, as well as the pseudo PN sequence based direct sequence communication system, combination of all these three. And the intrinsic forms of these transmitted signals corresponding to this first two type of these space spectrum modulation systems, where the frequency hopping will be given by like this, where your th will be the hop time interval, and your nt will be the total number of the hops in the space spectrum bandwidth that over which space spectrum bandwidth over which the hopping is getting performed. For FHPN, I mean frequency hopping and direct sequence combined hybrid scheme, the transmitted signal format should look like the expression 1.3, where the CT is the extra term brought, which is a PN modulation. The pseudo noise is the contribution coming from the pseudo noise direct sequence PN sequences. Direct sequence modulation and PN modulation is incorporated here. TC will be the corresponding chip duration of the chip sequence utilized for the direct sequence space spectrum communication. And please note here that the hop frequency spacing will be 1 by Tc, which is a factor of Th by Tc times larger than the pure frequency hopping. So when we are combining two schemes, we have discussed this earlier that the spread bandwidth and the hence associated space spectrum gain will be more for the hybrid system compared to the single kind of space spectrum modulation. So though basically the time hopping space spectrum modulation type of system is of also interest for practice, but here we will mainly continue with these two modulation schemes for the LPI applications. One is the frequency hopping and another is the frequency hopping space spectrum communications. So that was the signal format. Now let us enter into the interception detectors. Now if I change the focus from the intended communication receiver requirements towards the interception detectors, the great amount of effort and also the literature, you will find that people have discussed about what should be the property, what should be the configuration, what should be the performance, and the implementation issues of interception detectors. And going by all of them, in general you will be able to see there are basically the detector topology and the optimum configuration, the methods, and for their performance analysis, they are actually getting discussed mostly on the papers. And Some necessary foundations will be provided and some boundary criteria for the detectability they will be provided, and this detectability criteria for these interceptors will be mainly dependent on the parameters, certain parameters. The famous parameters are these. What is the detection signal to noise ratio? So detectability will see that a function of this SNR. It will be also a function of the total message time or the hop time, and it will be also a function of the space spectrum bandwidth or the hopping bandwidth spacing. So whether you will have a choose of TM or TH and WSS or WH, that is actually between these two basic approaches to detecting the hop signals will become actually shortly, which will be clear when we will go in deep. So whether we will go ahead the design with TM or TH or WSS or WH, which way which will be better to go ahead with for the design of the interceptor detectors, we will be knowing shortly. So fundamentally the learning is that if I am thinking from the interception detector design side, we will be really very important to improve the detectability, and hence our eyes should be over these parameters when the detector will be designed in the interceptor detectors. So the motivation is two-way. When you are designing the actual communicator receiver, then there will be your statement or problem statement will be to design the modus signal and the systems in such a way that it cannot be detected. But when you are designing the interception detectors, your target will be to maximize the detection probability. So it is two different way. Ideal and the realizable detectors. Basically we will start with that, then slowly we will try to go ahead with the realizable and practical detectors available. It presents the most pertinent aspects of these endeavors, and some merits and some basic detector configuration also we will be discussing on. Please remember, whenever we will be talking about the detectors, we will assume that there is a perfect frequency and time synchronization to the received signal structure that is happening, and mostly we will be based on the detector. We will be focusing on the detectability criteria, and we will be focusing also on the maximum or bounding performance of these fundamental detector types. So based on these two parts, we will be assessing the detectors in the upcoming slides. And remember that there is no assumption made with respect to the knowledge about the randomness of the space spectrum signals, space spectrum states, because when you are designing the detector, you cannot put any restriction of the kind of the modulation will be used on the space spectrum communication itself. So the detector design will be, that's why it will be always criticized with respect to the detectability criteria and the bounding part, maximum or bounding performance of the fundamental detector types. The detectability criteria, what do we mean by that? The task we have understood that the task of the interceptors will be to detect the presence of the communicator's transmission, and also try to at least attempt to identify roughly the communicator's location within a specified geographic area. And since the communicator's message or the transmission is not time continuous, and it occupies over a brief interval, because that you will try to do, because if you continue for a long time, if you go ahead with a long time message transmission, then there is high probability that somebody can intercept you. But if you go ahead with a short message duration, that we prefer for this kind of situation or in the hostile environment, and there it is a hard little bit for the detectors to detect it. So detectors are never going to get a time continuous signal so that they can refine their detections. And the interceptors desires, that's why they need to have a highly accurate detector to be designed for them, and there should be high probability that such short messages will be detected. So given the short messages, your probability of detection should be very high. So PD we prefer to be very close to unity. So on the other hand, the interceptors doesn't want this equipment to indicate state of the signal detection, and so for example, if I am trying to say what exactly the typical value of the detection probability and the false alarm that is preferable for the practical use, it will be of the order of detection probability will be at least 90% and probability of false alarm should be as low as 10 to the power minus 6 for the interceptor detectors to be designed of. Now coming in the maximum or the bounding performance for the fundamental detector types, we understand if you go for the exhaustive literature search, we will be finding out that almost all the detectors, the Hop signals, fall on the two basic type of the approaches. One is they try to deploy a wideband radiometer which are matched to the transmission bandwidth of the transmission signal, which is the WSS, and then they try to integrate this over the entire transmission TM. So your detector is a wideband radiometer basically. Otherwise, there are the multiple narrowband radiometers whose filter bandwidth and the detector integration will be over the hopping bandwidth and the hopping duration. So both the way the detectors are available in practice, but remember that when the second approach will be implied, its generic form will be such that the requirement of this filter, a requirement for the filter at each of these possible hop frequencies will be required, and number of the filters that you are trying to implement will be definitely very high. So this is dense with the hardware. This is not dense with the hardware, but it is actually integration time you have to be very large, and its processing time also will be very high. And we will go ahead with the comparative study of these two kind of the approach, and the basic difference that with these various structures will be how they are realizable. And it seems that the second approach centers on the decision procedure, which will be using for the every hop pulse detection data and into the decision of the presence of the transmission. So the approach itself will be different for the every hop duration wise. Here in the second case you will be trying to detect, and here you have to wait for the complete transmission over the whole bandwidth, and then we will be able to detect. So based on the applicability and based on your application and the kind of the detectors you are asking for, both of the approaches are possible to design. So in this, let us find out actually in the summary wise how many types of the detectors are available, interceptor detectors are available, and what are the relative practical values and the applications. We started with the wideband energy detector. We also called it the wideband radiometer. If you see actually what are the relative practical values, and they are very much functional, they are in the generic type of the use. Coming to the second option of the detector, second type of the detector talks about the optimum multi-channel frequency hopping pulse matched detector. These are very much theoretical detectors, or academic I should say, and they provide as an optimum performance bound. So it seems that whatever the performance bound theoretically you will be having using the optimum multi-channel frequency hopped pulse matched detector, none of the other kind of the detectors can give the better performance than this. So in that sense, this number 2 is a theoretical bound for on the performance of the detectors, because it's a match filter based. Next comes the maximum center filter, maximum channel filter bank combiners. They are the suboptimal version of this pulsed match detectors. Then comes the partial band FBC, and partial band FBC is the fifth one. That comes the partial band FBCs, which is actually some sub configuration of this number 3 or the FBC type. There is another kind of the detector which comes in between FBC and PV-FBC. This is the optimum, the partial band frequency hopping pulsed match detector, which is the realizable version of this number 2 I should say, but it is a complex sub configuration. It is realizable, but it is complex. Its complexity is little bit reduced than 2, but it is higher than the number 5. So these are all the kind of the detectors available in literature and discussed in the several books also. And out of all those five, the realizable detector structure will be only the TBFBC or some optimum partial band frequency hopping pulsed match detectors. And in between these two, actually, the one is also there in use, but preferable use will be the TBFBC. And we will see actually the different kind of the detector architectures and the structures in the very next module. And almost all these kind of the detector types will we keep on discussing in the next module.